All right, let's jump right in. Today, we are taking a journey deep into the subatomic world to look at exactly how the fundamental forces of the universe dictate energy generation. We've got some seriously fascinating physics to unpack.
In this explainer, we are going to focus on solving a very specific central mystery. We need to critically examine the statement, a fertile material has a threshold energy for fission, and figure out if it's true or false. Now, I know that sounds like a bit of a mouthful, but stick with me. By the end of this, you're going to understand exactly what that means, and honestly, why the answer to this question essentially holds the key to humanity's energy future.
To actually crack this case, we can't just skim the surface. We need to dive right into the nucleus of the atom. We'll be looking at actual cross-section data and quantum mechanics to see how neutrons really interact with heavy elements like uranium. So let's get started with Section 1, the F words of nuclear physics. Before we can solve our mystery, we really need to untangle three terms that sound almost identical but mean very different things. First up, we have fissile. These are basically the rock stars of a nuclear reactor. A fissile nuclide can be split apart by a neutron with literally any kinetic energy. We're talking even a slow, zero-energy thermal neutron. The most famous example here is uranium-235. It is actually the only naturally occurring fissile nuclide on Earth. If a slow-moving neutron merely taps it, it splits, releasing a massive amount of energy and tossing out more neutrons to keep the chain reaction going. It is incredibly easy to split. Now, the second term is fissionable but non-fissile. These materials can undergo fission, meaning yes, they can split, but they are incredibly stubborn. A slow neutron just won't do the trick here. They absolutely require a high-energy, fast-moving neutron to literally force them to split apart. They need a running start, so to speak. And finally, we have our third term, which is the entire focus of today's mystery: fertile. Fertile materials, like uranium-238 and thorium-232, are absolutely brilliant. When a slow neutron hits them, they don't break apart at all. Instead, they capture the neutron, absorb it entirely, and through a sequence of radioactive decay, they literally transmute into a brand new fissile fuel. It's kind of like turning lead into gold, except this is real, documented physics. Now, it's worth noting that uranium-238 happens to be both fertile and fissionable, but it is absolutely not fissile. To put it simply, our fissile U-235 needs virtually zero kinetic energy to split. It's just primed and ready to go. But our fertile U-238, which by the way makes up over 99% of naturally mined uranium, is way harder to break. For it to fission, it clearly needs an extra push from a high-energy neutron. So why the huge difference? Why is one so perfectly easy to split and the other one so incredibly stubborn? Let's find out in Section 2, the physics of the barrier. If we look at the Bohr-Wheeler fission barrier, you can picture a nucleus a bit like a drop of water, resting right at the bottom of a parabolic well. To split that drop, you have to add enough energy to push it up and over the edge of that well. We call that edge the fission barrier. And for both uranium-235 and uranium-238, the height of that barrier is approximately 5.7 mega-electron volts, or MeV. That is the physical hurdle they both have to jump in order to split. Now here is where the math gets really interesting. It all comes down to the Q value. When U-235 captures a neutron, the internal binding energy that gets released, thus the Q value, is 6.5 MeV. Since 6.5 is obviously greater than that 5.7 MeV barrier, it easily hops over the wall and fissions, no problem. But look at our fertile U-238. When it captures a neutron, it only generates an internal Q value of 4.8 MeV. That is less than the 5.7 MeV barrier. It falls completely short. Therefore, for U-238 to actually fission, the incoming neutron must bring in extra kinetic energy from the outside just to make up that difference. It absolutely requires a threshold energy to allow for above-barrier excitation. So we've got the theoretical math down, but we really need hard evidence to be certain.
That brings us to Section 3, the cross-section evidence.
When we look at the neutron-induced fission cross-sections for these two, the difference is night and day. The data for fissile U-235 shows a continuous reaction rate. It reacts and fissions even at incredibly low neutron energies. But then you look over at our fertile U-238. At lower energies, the probability of it undergoing fission is practically negligible. It's just flatlining down at the bottom. But then, as you move up the energy scale, boom, right around 1 MeV of incident neutron energy, there is this massive, sudden step increase. That step right there, that's our smoking gun. It is the definitive visual proof that a fertile material like U-238 has a required threshold energy for fission. Below roughly 1 MeV, it barely fissions at all because it simply does not have the energy to overcome that 5.7 MeV barrier we talked about earlier.
Which leads us perfectly into Section 4, the magic of breeding.
So what magically happens when a neutron hits our fertile U-238, but it doesn't have that 1 MeV of kinetic energy? Like, what if a slow neutron just bumps into it? Well, if it doesn't have the threshold energy to cause a fission, it kicks off this super cool 3-step process known as breeding. Because remember, fertile materials are defined entirely by their ability to capture a neutron and transmute into fissile fuel. Let's walk through these 3 steps.
Step 1 is neutron capture. Our fertile uranium-238 nucleus gets hit by a slow neutron. But because the neutron lacks that threshold energy, it doesn't split the atom. Instead, the U-238 just swallows it whole. Adding a neutron changes its atomic mass, instantly transforming it into a heavier, highly unstable isotope called uranium-239.
Now, because U-239 is so unstable, it can't stay like that for long. Within about 23.5 minutes, it undergoes its first beta decay. It spits out an electron and an antineutrino, and in doing so, one of its neutrons actually turns into a proton. It is literally no longer uranium. It has just transmuted into element 93, which is neptunium-239.
But guess what? Neptunium-239 is also highly unstable. So over the next 2.3 days or so, it undergoes a second beta decay. Another neutron turns into a proton, bumping it up to element 94 on the periodic table. And here's the grand finale. It turns into plutonium-239. We have just successfully bred a brand new, fully fissile, high-value nuclear fuel out of a rock that was otherwise incredibly hard to split.
All right, let's wrap this up in Section 5, the final verdict. We've gone over the quantum math, we've examined the cross-section charts, and we just walked through the subatomic chemistry of breeding. Let's put all the puzzle pieces together. The absolutely crucial point we've established is that fertile materials like U-238 only generate an internal Q value of about 4.8 MeV when capturing a neutron. That falls well short of the 5.7 MeV fission barrier. Because of that, they absolutely require external kinetic energy, specifically greater than a threshold of roughly 1 MeV, just to breach that barrier and split. And if they don't get that energy, well, they follow their fertile destiny and beautifully breed into new, perfectly fissile fuel like plutonium-239 or uranium-233.
So, returning to our central focus for today, we set out to carefully examine the statement, a fertile material has a threshold energy for fission, to see if it's true. Well, we can now say with absolute, undeniable certainty, backed up by the fundamental laws of physics, that this statement is officially true.
And honestly, this brilliant reality of physics leaves us with a mind-blowing question to ponder. Since natural uranium is over 99% fertile U-238, our conventional reactors today only extract energy from the tiny 0.7% that happens to be fissile U-235. But if we design breeder reactors that utilize this exact threshold physics to continuously breed new fuel, we could multiply the energy we extract from raw uranium ore by a factor approaching 60. Think about that for a second. We could extend humankind's clean energy resources by 50 to 100 times just by leveraging the incredible threshold physics of fertile materials. What does humanity's future look like with that kind of virtually limitless clean energy? That is something truly amazing to think about. Thank you so much for joining me in this explainer today. Keep asking questions, and I will catch you in the next one.